Hello, everyone. Thanks for joining us on our OffensiveCon watch party on YouTube. It's a bit of a different experience because, yeah, this is the first time we've streamed on anything other than Twitch. But um, yeah, so because of that, we're starting a few minutes late, just trying to get things set up properly. But yeah, so we're going to be covering some OffensiveCon talks today. We've got two of them lined up. First one is Counter-Strike Global Offsets. So that's going to be talking about popping Source Engine, I believe, getting RCE through CSGO, which, hacking through games is a pretty fun avenue. So I think it's going to be a cool talk. And then for the second talk, we have a Project Zero talk for data-only sandbox escapes, which I think might overlap a little bit with a topic we covered on the podcast. Though I'm not sure, but the title suggests that it might. But yeah, we'll see when we get there, I guess. But yeah, like I said, thanks for everyone who joined us, and I guess we'll get started here on the first talk, which is by Simon Scannell, Nicholas Bretfeld, and Carl Smith. And yeah.
Welcome to our talk, Counter-Strike Global Offsets, our journey into
And
exploiting the
I'll
source engine.
apologize if it's coming through pretty
Today we're going to
quiet.
talk
That was
how
part of our
Counter-Strike
audio issues, and
2022
I can't get
started.
it much better than this.
So first off, I wanted to talk a bit about motivation. So Counter-Strike Global Offensive has a huge following and lots of players on Steam every month. Additionally, it also has like a very lively esports community. There's already been successful prior work, which in combination with the older source engine has lots of potential for some juicy bugs. So we also started this work a bit more than a year ago as a pandemic project while we were all at home. There was also a public leak of the source code on GitHub, which has proven to be very helpful. And we also played it extensively at some point in our lives, and we thought like it would be super cool if we could pwn it. So yeah. So what is our attack scenario? We specifically focused on server-to-client vulnerabilities as the server-side code was already like thoroughly audited, and also it seemed quite robust. Yeah, there are lots of community servers. Everyone can like host one, and even during our testing, players joined our server at random. I think we also crashed someone at some point. And yeah, so this definitely seemed like a realistic attack scenario. And well, yeah, once we have pawned one client, we can also iterate through the player's friends list and just send out crafted Steam invites to make them join our servers and pawn them as well. To give you some background, we first need to cover like the setup and some of the tooling that we built specifically for this project. So the client uses a so-called information concealment engine, like a symmetric block cipher for encryption. They only perform a real key exchange on official servers, and on community servers, the key is always hard-coded and tied to reversion. Because apparently they prefer to write their own like networking protocol on top of UDP for speed improvements, the baseline networking code includes like fragmentation layers and also supports compression. On top of this, like
So I'll comment on this really quickly. This is one of the fascinating things about Steam and about like how Valve game works in general. They basically have like their own CDN and like networking protocol. It's pretty insane what's going on under the hood with Source Engine and the networking side of things. So yeah, I guess he's kind of getting into that now with like how there's the fragmentation and all that. But yeah, Valve basically has their own like internet, for lack of a better word.
Yeah, and I mean, in fairness, when it comes to gaming, like a lot of custom networking stuff is kind of the common way to go about it. But of course, Steam's fairly well established, fairly old. Um, yeah, I don't know where I was going with that comment actually.
Yeah, I
But
mean
it
it's
is,
just because perp is so critical with gaming.
yeah.
So yeah.
Yeah, no, just on the age aspect though, like I feel like there's probably a lot of cruft within Steam just because of the age. You know, technology and approaches change, but he hasn't really gotten anywhere where that's relevant, so I don't need to dive into it.
this like adjusted UDP protocol, the main method of communication is via protobufs, where they exchange like messages of various types, which are either bidirectional, only from client to server, or only from server to client. We explicitly target these messages and we'll be making references to them throughout the talk. So we built a proxy that allows us to inspect, dump, drop, or even modify these messages in real time. And it has been super helpful for analysis, testing the vulnerabilities, and subsequent development of exploits. So here's like a short demo of the proxy in action. On the left-hand side, you can see the player moving, shooting, changing weapons. And on the right-hand side, you can see the messages that are being like, yeah, that we captured in real time, basically. Yeah, so the source engine was released way back in 2004 and is mostly written in C++. So this already sounds super promising. Security back in 2004 was quite different to like modern security practices. So most prominently, there was like a classic stack buffer overflow in the parsing of encryption parameters. And it has been since fixed, but since Counter-Strike is also compiled without stack cookies, it makes exploiting these kinds of vulnerabilities rather easy, especially in the past. There are various lines of codes that do not seem to be actually used in the game. The whole architecture of the game is quite complex, and it's definitely not immediately clear what code is responsible for what. The developers also use lots of asserts, which they sometimes use for balance checking. Fortunately for us, those asserts do not actually end up in the release build. So this made finding some of the out-of-bounds accesses very easy. So lesson learned, do not use asserts for bounds checking. If they are definitely not, if they're compiled into release builds, not compiled into release builds. So now I'm gonna hand over to Simon. He will talk about the first bug, the info leak.
Okay, thank you, Carl. So, although there were some decking mitigations, we still needed to break ASLR, which is why we started looking for an info leak. And to start explaining this bug, I want to give you some background, just to have some context in order to understand the info leak. So CSGO has a problem, which is that anyone can host a community server with maps that are not typically shipped with CSGO by default. Those are your surf maps or hide and seek or whatever you want to play. And they might ship with some game assets that the client does not have. Now, this is a problem, as every time the CSGO server changes the map, all players that don't have the map downloaded would get disconnected. And as you can imagine, that could be quite frustrating if you get disconnected like every 10 minutes. The solution to this problem is to enable players to dynamically download maps at the beginning of each round. The way this works is that the server sends the client a HTTP URL during the connection stage from which to download files from. And we actually discovered a path traversal bug in the download functionality, but it turned out to be a duplicate, which is unfortunate. But we further investigated and found an interesting parser differential.
I'm a little bit surprised by that they would have like really such a trivial directory traversal so early in it, like something that I would have thought have been pretty well tested or at least thought about.
Yeah, when you start getting to the server side, yeah, it's a little bit surprising for sure.
Yeah, I guess I'm maybe not sure how this path traversal works, if this is with the client downloading it and where it places the file it downloads, or if this is server side. I kind of just assumed this was client side. Like an RC client side, because it's in the download logic.
Oh, true enough. Yeah, sorry. I was thinking it could be, yeah, I was thinking path traversal in a server context. I guess just because that's where we see it more often than not.
Yeah,
But yeah,
I mean,
that makes sense too.
regardless, it just feels like a very silly issue to still have sitting there. I wonder how long it's been a duplicate for, too. They're just not fixing it, don't care.
Yeah. Fortunately, probably never know.
Bug that led to a powerful info leak. So with the next slides, we'll break down the high-level logic flow of the download functionality as it was implemented on Linux. CSGO also works on Linux, which is cool, and we prefer working on Linux as we're more familiar with it than Windows. And I will come back as to why that is important in a couple of slides. So at the beginning of each match, the server sends the client a list of files that are required to play during the current match, whether that is sounds or skins or any other game asset you could think of. And the client then simply concatenates the missing file name with the HTTP URL they received during the connection stage. The download is implemented using libcurl on Linux. Now let's look at some reverse code and interesting behavior. When CSGO set up the curl request, it registered a callback that is called for each header in the HTTP response. This is the curl header callback you can see here, and it basically just receives a pointer to the header, and that's it. And then there's also a curl write callback, which is called when the HTTP body is received, which contains a pointer to the buffer containing the body. Now looking at the code of the curl header callback, we can see that there's a case-sensitive compare against the header name, and if it equals content length, a branch is entered. And we'll discuss what happens inside of that special branch on the next slides. So we have just seen that the content length header is processed and interpreted by CSGO. The value of it, which is an integer, is used by CSGO to allocate a buffer that is large enough to fit in the HTTP response body as given by the HTTP server. The buffer is then written to disk with the desired file name via the write callback. So now for the parser differential. On Linux, the CSGO client parses the header case sensitive, but the underlying library, which is curl, case insensitive. This naturally leads to confusion between the two. If we now tell CSGO, the CSGO client, to create a large buffer on the heap by setting the content length header to an arbitrary value, but then just not send a body or an empty body, the CSGO client will happily write uninitialized memory to disk. So
Not going to lie, I mean, I've said this quite a few times during our podcast, but I love when we see these parser differentials. They're just such fun bugs to see introduced. And I mean, completely understandable why devs don't necessarily think about it. Like, I don't blame any dev for not realizing the difference in how things are getting parsed at all, but they're always so much fun to see. I mean, I don't know where he's going to go with this one beyond. Well, I guess it is just the info leak, so maybe he won't use it for anything more, but maybe they will.
Well, what I'm assuming is going to happen is that the one length is going to be used for allocating the buffer, and the other one's going to be used for filling it. So you could end up with like an out of bounds.
Well, he just mentioned it's an uninitialized.
Oh, right. Sorry, uninitialized.
Yeah.
So yeah, it's probably you're probably ending up in a situation where it thinks the size is less than it is, so it doesn't fill in enough bytes or whatever.
Yeah, that is what he mentioned already. I just meant like I'm interested to see where he goes there, if there's going to be more to it in the exploit, but odds are, since this is the info leak, it's just going to be used for an info leak and, not too much more. I know on the web we'll see this get used in some pretty creative ways. Oh no, they're fun to see. I like these parser differentials because they are often kind of subtle but rather impactful depending on what's actually where the differential exists. Anyway, let's let him.
Well, I will say, like, out of all places, desync, like, to see a HTTP desync bug, like, I didn't think it would be in CSGO like this. But another thing I'll comment on is you were kind of talking about using it for an info leak here. And one thing I'll point out for Source Engine is one of the interesting things with Source Engine and bug hunting is you will find lots of really stupid memory corruption bugs that will allow you to take like code execution or do something useful. But what often ends up hindering you or bottlenecking your exploitation efforts is the need for an info leak, because obviously this is remote, it is happening like server to client. So you kind of need an info leak to be able to take advantage of memory corruption, and that is often like the harder part of the chain for popping something like CSGO. So yeah, even though this might not be like a super clever way of taking advantage of the HTTP desync bug, it's very important for the chain, that's for sure.
Yeah, it's interesting that you mentioned the info leaks are harder. It just makes me think about, like, with fuzzing, we're often looking for the crashes. You can with CSGO, you're not really going to be able to compile in a sanitizer to help you out, but we don't have like really strong a lot of really strong detection mechanisms for just an info leak. You do have a bit with ascent if you can compile that in, which you're not doing with source. Sorry, you're not doing with Source Engine. If you have source code, you can't do it. So yeah, I guess that does make it a little bit harder because you have a less obvious error condition to actually know you're leaking something.
A bit more. Here's an example HTTP response sent by a malicious server. So as can be seen, 2 content length headers are present in response. And the first time it occurs, it uses capital letters and has the value 1337. And the second time it occurs with lowercase letters and has the value 0. So CSGO only recognizes the first header and allocates a buffer of size 1337. Curl, on the other hand, expects an empty body now that it recognized the second header and uses it as the value, and then proceeds to write the buffer to disk, and it doesn't return an error. And this file will now contain uninitialized memory. That is because the call write callback is never actually called because the body is empty. So now to Windows. On Windows, they use an entirely different HTTP library, and they actually used completely different code, but the same proof of concept that I just showed you, actually worked on Windows without having to be modified, which was kind of cool. And So on Windows, instead of curl, they use the built-in Windows Internet API, and they used a couple of functions. So first, they would open a client resource with Internet Open, and then they would open specifically HTTP resource with Internet Open URL. And then they use that resource to make the HTTP request with Internet Read File. And then some interesting things happened where they used HTTP query info on the resource to gather some information about the request. For example, you could request the values of some headers. And in this case, they used HTTP query info to retrieve the value of the content length header, similarly to the implementation of Linux. Now, what was interesting is that Windows didn't complain when we retrieved that value. And actually, the real size of the body is returned by Internet Read File instead of HTTP query info. So again, they did not compare the values and use the wrong value without a body ever being received and written to the body buffer and wrote that file to disk. So in order to break ASLR, we can now spray the heap with objects that contain function pointers and then deallocate them again. And luckily, the CSGO process did not clear allocated memory when it was allocated or freed. This means that the buffers that were written to disk would contain anything that was written to the memory beforehand and then freed again. So you have to keep in mind, though, now we have files on the client of arbitrary size, that contain uninitialized memory, including some juicy pointers. But they're stored on the client's disk. So now we had to find a way to retrieve those contents from the client's disk. And we thought, okay, maybe we'll have to find some super sophisticated side channel leak or any way to leak the files. But as it turned out, it was very easy because, funny enough, the CSGO server can just ask the client to upload any file that is in the CSGO directory. We assume this was done to verify some files on the client. And instead of uploading a hash of the file or CRC or whatever, they would just upload the entire file. This meant we could just parse the file, look for some pointers that we were looking for, which contained some function pointers to the base image, and we broke ASLR. And the info leak was 100% reliable. We tested it many times, and it almost worked every single time on the first try. And even if it didn't work on the first try, you could just retry it an infinite amount of times because you didn't actually corrupt the client's memory, and you could just ask them to re-download the files again and repeat the whole process. So now that we had a reliable info leak, we're ready to corrupt some memory, which is what Niklas will be talking about next.
Yes, thank you, Simon, for the info leak. So obviously, we also need some way to corrupt memory. And it is to say, while we tried the following methods to find bugs on both server and the client side, we were only able to find bugs on the client side. The server side has already been pretty hardened since source leak in 2020, sorry, and didn't yield us with any bug whatsoever. So to get a feel for the networking attack surface, we utilized our networking proxy and started to modify with some of the protobuf messages and played around the values a bit. So, and this showed promising results as we are able to find quite a few issues. Sadly, however, the majority of bugs were simple null pointer derefs, and which is not in our interest as we were hoping for an RCE, and crashing the client is not really a security concern, at least not for us. However, in the end, we found quite a neat out-of-bounds access bug, and yeah. So additionally, we also used knowledge that asserts were not compiled into the release build and manually audited
I will mention, just in general with auditing, I mean, it's not necessarily the best practice to only just grep and look for code places, but grep is a completely valid static analysis tool in my opinion. And grepping for asserts, especially if they're not getting compiled in, is a pretty fair way to go about that. I mean, you can probably Google and find plenty of lists that have other things you can grep for, dangerous function lists, or so to speak. But I mean, we've covered actually a few issues where the core issue has just been the fact the assert would have caught it, but the assert isn't compiled into production. So I mean, it's a fair approach here.
Seems to be a big issue with legacy code. I don't know why, just a lot of older code was written so that, I guess because they didn't really consider them security issues at the time, or the security implications weren't well known. So it was just like, okay, well, let's try to catch if this is an issue in debug builds, but then otherwise we don't care. But yeah, I mean, obviously, years later, that's coming back to
Oh no,
coming back to roost.
I think we've seen it in like Chrome, which isn't exactly legacy code. I think it's used everywhere. Like writing tests that can be just compiled into debug is a pretty common. Like actually, when I was in university, we were taught to do our test case to write them as these asserts so they wouldn't be compiled in. Granted, that was specific, like the actual test setup that we were using, and that's not really a robust test system by any stretch of the imagination. But that was kind of the process we were taught, and it is reasonably common to do that. I'd even say with modern code.
Yeah, so I'm not trying to say that it never happens in modern code, but it is like a lot of the ones we covered on the podcast were from older code in like Windows or whatever. It does seem to be more common in older code. It's not as much of an issue. I guess it's kept in mind more when modern code's being written. But yeah, I'm not trying to say that it doesn't exist at all in newer code.
Perhaps, yeah. I mean, I don't know the stats for if it is more common in legacy code. My intuition is saying that it's common across both, but you know, whatever. I don't actually have any stats to back that up, and I'm not sure if you've got for your side, but it's just kind of
No,
an intuition thing.
I'm going kind of anecdotally based on like what we've seen in the podcast and whatnot. So yeah, I don't have hard stats backing that up, but
yeah, and I don't either. I'm not calling you out for not like, where's your paper? You know, where's your scientific research on that? No, I mean, simple fact of the matter is looking for bugs this way is completely fair and not a bad idea at all.
yeah, sorry, I'll have my white paper filed soon.
The source, and that also yielded us with an interesting bug. So one of the out-of-bounds access was in split screen control. To give you some context, the source engine is able to have a two-player split screen session, which can be requested by the client. And the bug is triggered by the split screen control message sent back by the server, and you can see that on the left-hand side. This is to acknowledge the split screen request from the client, and the client uses this message to set up the split screen session and some metadata around it. However, no check on the client is performed if the client has actually requested a split screen session in the first place. So the attacking server is able to send that control message at any time, and the client will happily comply and set up the thingy. So on the right-hand side, you can see an image of the vulnerable code, and the end slot is basically the slot index in the put above message, which is unmodified and unchecked whatsoever. Right. So the array we can perform this out of bounds on actualizing the data section. So we have to keep that in mind when we develop the exploit. And also you can see a few lines down the code that virtual call is performed, so we have PC control almost instantly. So to take advantage of this issue, we first need to find a way to place a pointer to controlled memory inside the data section. And luckily for us, the source engine provides us with just the right primitive, and that's CVARs. CVARs, or configuration values for short, are fixed named config values which are part of the bidirectional protocol. For those of you who played CSGO, like setting your crosshair or view model, that's also a CVAR. And they can hold all kinds of types, such as strings or floating points or collars, which are actually interpreted as integers, which is important for later. And the server has actually the ability to set and read CVARs to its liking. So because only a fixed number of predefined CVARs actually exist, they are also stored in the data section, and this is exactly what we need. So in case the CVAR is a string, a pointer will be placed which points to the heap. And the best part is that thanks to the way values are updated, the server has the ability to write null bytes into those strings as well. So the client will only reallocate the buffer if the updated string is bigger or it wasn't a string before. So by repeatedly sending the payload in shrinking chunks, splitting at every null byte, we were able to place any memory we wanted into the heap word server. And that's actually really important because sometimes due to ASLR, it could be that the base image was placed at the section where null byte was in the pointer, and then the whole exploit wouldn't work. So, and we additionally use another trick with CVARs, and that has to do with the color attribute. And we needed that to place a control pointer. Like with the string, we can only control the contents, but not the pointer, but we also needed a pointer. So, but contrary to pointers, the integer values are first obscured before they are stored. You can see that in the screenshots on the right. And a comment in the source engine actually tells us that this was to make it harder to find the value in memory using cheat engine. And that could have proved a tough roadblock for us actually, because we had no way to predict the encoding. However, thankfully, the encoding was done via the disk pointer, and because we leaked the base image with the info leak already, we can predict the encoding and so still place any value we wanted into the.
You know, I'll mention, I don't think I've really seen this done before. I wouldn't be surprised if other games are doing it. I haven't been all that involved in the game hacking scene. Like, it makes sense, but I do think it's interesting that they are kind of obscuring the values that way.
It's kind of funny that like an anti-cheat feature in this way is also doubling up as a like a mitigation in a sense. It's kind of neat.
Yeah, I mean, I feel like a lot of anti-cheat stuff can double as that, though. Because I mean, ultimately, you're still kind of messing with memory, so it still does act with or it still does act to create some hindrance, or at least some sort of thing you need to get around, even if it's not like a strong mitigation. It's still kind of unique, and those unique situations do kind of toss wrenches into the exploit dev side of things. And yeah, the flying object mentions in chat there, interesting type of pointer encryption, reminds me of safe linking in libc. Safe linking, that's when they were doing the was it XORing the upper bits of it? Or I don't think they were XORing the whole thing, or were they? Oh no, I think we covered a safe linking thing on the podcast.
We did, yeah. If I remember correctly, it was basically like pointer authentication before pointer authentication was a thing. Like it was kind of doing that kind of idea.
Well, I think pointer auth already existed over on like iOS, over in like ARM land.
Yeah, I don't remember exactly. Yeah, I guess it's been around for a while. So, but yeah, basically the same idea.
Right. Flying object mentioned shifting the ASLR, so where it gets where ASLR the randomized base address, shifting that down and XORing the address with it. Yeah, now I remember it a bit more.
The memory. So if they used a random value, that wouldn't have worked. So let's have a quick overview over the game plan. So the first error is the out of bounds access of the split screen array, and this will point to the fake string or the CVAR string object, which will point to our fake object on the heap. So now we have to create a valid virtual table for the virtual call to take PC control, and we use the second CVAR to write a single jump gadget and point it to the so we pointed the virtual table to the second CVAR we used as with the color object to point it to a single jump gadget inside the main text section. And then we just pivoted into a ROP chain, and I will talk about that now. So thanks to the nature of virtual calls, we have at least some context to play with, or some registers. In this case, the disk pointer is stored in ECX, and because our fake object is entirely controlled, we have a pointer to memory we have chosen beforehand to our advantage. And actually, while we were developing the exploit, while multiple updates were released to the game, which is quite rare, so we were quite unlucky, and sometimes gadgets were added or removed. So in a few cases, EBX also pointed to the fake object, and that simplified the jump chain quite a bit. So in both cases, we pivoted the stack to the fake object, as this controls a good chunk of memory suitable to holding a ROP. So in the first one, we first need to exchange ECX with EAX and then do the pivot after an additional jump gadget. And in the second one, we were able to pivot immediately. So, and for the ROP chain, we just used the generic ROP to system or shell execute A, depending on the OS, which is enough to give us control over the client. So let's have a quick demo.
Yeah, let's maybe watch it a second time. Yeah. So what is the actual impact of this bug? Well, we can reliably execute code on the victim's machine. So the info leak can be performed multiple times until we are certain that we have all the pointers that we need. And the out-of-bounds issue is, and the memory corruption are also reliable, assuming the info leak is valid. So from here on, attackers could easily steal private information, stage malware, steal expensive keys, or install crypto miners. It would also just be as easy to send out more Steam invites to pawn even more people, or just use the PC as part of a botnet. So one more thing. Let's also talk about the disclosure timeline. So we have reported the bug through HackerOne on the 4th of January last year, and it was actually tried a couple of days later by a HackerOne employee, and then nothing happened for almost 3 months. So yeah, we already gave up on getting a bounty, and we hope to just get a blog post at some point. But then some other people actually published posts about Counter-Strike vulnerabilities on Twitter, and we joined them and published a video of our exploit as well. And then, after a couple of days, a couple of news outlets actually covered the vulnerabilities, which then apparently made Valve focus on the HackerOne reports, and we noticed that they were slowly getting fixed, and that gave us hope. Eventually our report was fixed, and we actually received $15,000 as a bounty. Yeah, but unfortunately, the communication was only through a HackerOne representative, and we never got any message from a Valve employee. Yeah, so this is the end of our talk. Feel free to ask us any questions.
Yeah, we talked about this before on the podcast. It's kind of funny. I was laughing a little bit there. It didn't come through on the stream because I was muted, but they were talking there about the timeline and saying how they were surprised it took 3 or 4 months to get a response from Valve. I know people who have submitted bugs to Valve HackerOne for Source Engine that went for over 9 to 10 months with no response. They're terrible for getting back to you.
They've had a pretty poor track record at times. Seems like they took some heat. I want to say last year, maybe it was in 2020 yet. That kind of seemed to start improving things a bit. But I think part of it comes down to, as I understand it, working at Valve or with Steam stuff is it's like this very open, work on whatever you want sort of thing. So of course, working on bugs is not the nice job to go and do. So people just don't choose to do it and choose to work on features or whatever. And it seems to have a little bit to do with kind of how they do their little corporate structure for developers and stuff.
Yeah, that's exactly what I've heard about Valve, is that it's a very loosey-goosey environment, work on what you want. And that's caused some problems with the game over the year. Well, with multiple Valve games, but especially CSGO. Beyond just security issues, even other things in the game that just didn't get fixed forever. Yeah, it is unfortunate, especially because when Valve did pay, they did pay pretty well. I think they said in this one they got $15,000. Some of the RCEs, when they got resolved, they were pretty nice payouts, and Source Engine was a very interesting target to look at for exploitation, because for those who like exploit dev over VR, Source is kind of the perfect target, because like I was saying earlier, finding memory corruption in Source Engine is not super difficult. There's a lot of bad code that you can look at there, but the exploitation gets a bit challenging. When you're talking about ASLR and requiring a remote info leak, it's just kind of a fun target to exploit. So if it wasn't for their stupid long response times and their problems at the HackerOne level, I would love recommending it as a target. Just from what I've seen and from friends I have that work on it. But yeah, the fact that Valve takes so long to respond and the correspondence is so poor kind of ruins it a little bit. So,
Yeah, the response time sucks, but like if you are doing the exploit dev, and you're looking to kind of maybe do a bounty as a way of getting some practice in, but like there is a huge divide. Like you can either go and sell end days off to or not end sell O days off to a broker, pays really well, but like they're paying very well because it's very difficult. Then you've got the other bounties from like Google and Android, or I think they offer some with like KCTF or whatever their container system is. They offer some bounties in there, Microsoft bounties, like very high paying bounties and very difficult. Like there isn't much in this in between beyond either that or like Valve and Epic Games on the lower end. So like there's still decent choices if you're trying to get some practice or trying to get some experience. I think Epic Games is the other one that kind of comes up for the binary. I mean, I'm sure there's some like antivirus that you can do, like some binary exploitation on their engines or something, but I don't hear about that as much. Ermac in chat does ask, can you make a whole detailed video on learning exploitation, like elementary to advanced? I don't think that's really possible. Not in a single video without it being insanely long and not really covering anything. I have put together a getting started blog though, or like a blog post.
I think the blog post as a format is much better suited for that.
Yeah, and I just put together.
It's just kind of tough for that.
I put together a bunch of resources to help get into the exploit dev. I've just put the link in chat. So my thought is you can't learn exploit dev just by watching a video. You have to get practice and you have to do the puzzle solving aspect of it too. You can't just do the walkthrough. So that's where I put a bunch of resources together in that, which give you both the educational side of like, here's how you get started and like the basic concepts, plus resource to get practice with. I will say, in terms of going from advanced, I have yet another blog series that kind of covers on going from about that level, which I'd say that gets you up to ROP, which is where I'd say is like your intermediate. All the advanced stuff starts becoming approachable once you kind of get the concepts behind ROP and the concept of gadgets and primitives. Which is where that getting started link kind of takes you. But I don't think we'll be doing a single or even a series anytime too soon on going from beginner to advanced exploit dev.
All right, so I guess we can move on to our second talk here, which is by some people at Project Zero, titled "Data Only Sandbox Escapes." It'll be interesting to see if they're talking about the iOS bug that I was thinking of that we covered on the podcast, because that was kind of like a data only sandbox escape, if I recall correctly. So yeah, might see a reappearance of that, and yeah, we'll get it started here.
Yeah, just dealing with the technical side here. It's a little bit annoying to get the change to happen, but all right, got it now.
And today we're going to talk about how we pawn CSGO clients with a malicious server. So first off, I wanted to talk a bit about motivation. So Counter-Strike Global Offensive has a huge following and lots of players on Steam every month. Additionally, it also has like a very lively esports community. There's already been successful prior work, which in combination with the older source engine has lots of potential for some juicy bugs. So we also started this work a bit more than a year ago as a pandemic project. While we were
wait, sorry. Are you guys still getting the? Yeah, I think that the global offsets talk is still coming through on the stream too. So I don't think it's switched over.
Yeah, actually, I just noticed that's playing the wrong thing. Sorry, I was trying to pull up the link for somebody in chat and wasn't quite paying attention. Let me try this again. This looks better, and that's also, I think, louder for everybody.
Okay, perfect.
All right, so let's try that again. And I apologize if this does come up loud. I'll try and balance it once they're talking.
Work as part of Google Project Zero. We both have been mainly focusing on Chrome research for the past few years. Today we're going to talk about escaping the sandbox in Chromium-based browsers, and more specifically, general approaches an attacker might take to exploit vulnerabilities in privileged browser components from a compromised renderer. So first, I'll give you a few examples of real-world sandbox escapes and describe one of our own latest full chains. And in the second, more technical part, Mark is going to present a new approach to exploiting vulnerabilities in privileged processes. So how do people escape the sandbox in Chrome? For many years, most real-world actors didn't even bother with attacking privileged Chrome processes. They would just go straight from the renderer to the OS kernel or a privileged system service, especially since their implants would usually require system privileges to work anyway. So such sandbox escapes are nice, they're reusable between browsers, for example. They live longer, we've seen them in the wild, and they are out of scope of this talk because they're not Chrome specific. Luckily, it looks like attacking the OS directly from the renderer is no longer in the path of least resistance, at least on some platforms. So maybe instead of working on the super duper secure mode, someone should work on stronger sandboxing primitives. But yeah, on some platforms, it is now easier to build a chain where you compromise the browser or GPU or network process as an intermediate step towards getting superpowers on the target device. And how do you do that? Well, occasionally, security researchers find bugs in privileged processes that can be triggered directly from JavaScript or over the network. And you can actually check out our blog about exploiting such a bug in the Project Zero blog. But most of the time, you're required to have a more precise control over what's sent to the privileged process to trigger the vulnerability, which means you have to compromise the renderer first. And let's look at a few ways attackers abuse the compromised renderer. This first example is from an exploit competition. Most of the exploit is written in JavaScript, but the JavaScript code has to live patch a number of native functions in the Chrome binary. So exploits usually do that for one of two reasons: to remove some render side checks in order to trigger the bug, or prevent the renderer from crashing in the process of exploitation. And the second possible reason is that you might need to modify some data that will be passed through an IPC channel in a way that's just impossible during the normal browser operation, like corrupt some length field where the length calculation is always correct in the renderer. And the main disadvantage of this approach is that the necessary modifications are unique to each bug, so it takes manual work to implement them, and quite possibly it takes extra work each time the browser is updated. There also might be subtle side effects which will reduce the stability of the chain, and most productionized exploits actually don't work this way. The exploit we discovered in the wild in late 2020 takes a different and more conventional approach. In general, in the wild, browser exploit chains consist of isolated, interchangeable components, since it makes maintaining the capability easier. In addition, it allows the attacker to do a bit of extra profiling from the renderer process and pick the most appropriate sandbox escape. So the renderer exploit usually doesn't provide an interface to a later stage. It doesn't expose an arbitrary read-write primitive or function call primitive. It just receives a binary blob with shellcode and jumps at the beginning of it. This exploit is a small handwritten binary that supports 4 major versions of Chrome. The developer had to maintain a list of version-dependent constants and a few bits of version-dependent code. So the exploit looks up a table of IPC functions known as the Mojo System API, and more on that later, and interacts with other processes at this level, which is roughly in the middle of the Chrome IPC model. The actor has definitely spent a lot of time on the sandbox escape exploitation framework, but there's still a fair amount of manual labor required for each new bug and exploit. Also, yeah, the exploit has to do things like going through 9 levels of indirection just to get an IPC handle. But that is just an unavoidable consequence of Chrome's code complexity. And the final example is also served to a target as a binary blob, but this one is much bigger. There's a small bridge layer that looks up a few pointers in the process memory and initializes a few structures. There is the core exploit logic, like the main function, but virtually everything else is just a copy of Chrome that's compiled into the exploit, to the binary blob.
So it's really cool here because we're getting some insights into like weaponized exploits that you don't really see with like people that are just publishing like quick browser exploit POCs or something, or if they're writing an exploit for like the Switch or like some console. Typically you'll have what he was saying at the beginning, like it'll just expose some interface with primitives like arbitrary read write primitives or whatever. And it's fairly like straightforward in what it's doing. But when you have these in the wild exploits where they're trying to take advantage of like system APIs in this way, it's just not something that you get to see as much, I guess, if you're not looking directly at in the wild exploits. So yeah, it's really cool to be able to see that insight here in this talk. Like the post exploitation side of things.
Yeah, I'm going to apologize to everybody who was just listening to that and not hearing anything I was saying. For some reason, my hotkey only unmuted me to Spectre and not to the actual stream. I caught that pretty quickly here, but I'll apologize for that. I was just mentioning that it's interesting also here to see to have a chance to talk about kind of the stability and portability of the exploits, because it is something that we don't often end up covering. And I say that, but during our last podcast, I made pretty much the same comment when we were talking about a Python 3 exploit. Python 3 being a much softer target. You're not hearing me now either? Sorry, in chat they're saying no voice. Oh, okay. I think the chat message was just a little bit delayed. Yeah, so anyway, jumping back onto this, I think things are fixed. So jumping back in here, like exploit stability, because when you're reporting a proof of concept, if you're putting something out like that, you don't need to dive into stability. You just need to show that this works and could be done. There isn't much talk about, well, how do you weaponize an exploit, because that knowledge starts getting into, should that really get shared? Like, it's not helping researchers at all to really get into that stability side if you're just researching. I mean,
Like
unless
if you're
you're
researching
weaponizing
with defense intent, like with defense as like your primary goal, then yeah, that's not really in your scope.
Yeah. So it's interesting to see it. It's interesting to have a little bit of insight into the architecture of like the productionized or weaponized exploit. And Flying Object mentioned, yeah, glad P0 gives a view into the production side of things, since these companies won't themselves. Yeah, and I've really appreciated the fact that Project Zero has been putting out the P0 RCA stuff, the root cause analysis of their in the wild exploits that they come across. That gives a ton of insight, what's actually going on. Or at least some insight into it. Obviously, it's what's going on that they're catching, so it's not everything that's out there, but it is some interesting insight nonetheless.
And it's the first time in my experience that recovering symbols in an exploit with bindiff was effective, as you can see on the screenshot. These nice C++ function names. There's likely a separate build of this exploit for every separated version. And interestingly, it seems like the most advanced framework with little to no manual work required per browser update. But, well, I hope you agree that 2 megabyte shellcode is not the most elegant thing you've ever seen. Yeah, these 3 examples more or less represent all the Sandbox escapes, or rather the Sandbox escape exploitation approaches we've seen in external exploits. Well, we don't like them. We want our exploits to be in pure JavaScript. So, story time. Why is this picture on the slide? Should one of the keynote speakers be concerned? Not really. There is tradition in the security and privacy teams at Google. If you live in the team or live in the company or moving to another office, like another country, you can challenge your colleagues to own you and steal your password. Your goal is then to defend yourself. This counts as a security exercise, and it leads to interesting discoveries. It allows the defensive teams to improve their detection, for example. Most importantly, just a fun way to, a way to have fun at work and actually use some of your 0 days. Time is usually a constraint in these exercises because not everyone announces their departure too well in advance, and the fact that the target expects you to tag them in the next few weeks makes it even more exciting. So a little more than a year ago, we learned that Justin Shu opted into the tradition. You might know him as one of the authors of this book, entitled The Art of Software Security Assessment, but Justin also spent more than a decade securing Chrome, so it naturally made sense to own him with the Chrome full chain. We knew that, as most Googlers, Justin primarily used his Chrome OS laptop. We suspected it might create additional challenges, well, and it did. So just a couple of words about the renderer bug. We tried to cut corners, obviously, and build an end-day chain first. So started by looking for recently fixed issues that hadn't yet made it into the latest stable release of Chrome. And Chrome OS actually helped us because it lags a few days behind behind other platforms. So, and as a lot of you probably know, the best place for finding fresh renderer bugs in Chrome that are easy to exploit is v8/source/compiler. Trugafan. This change immediately caught our attention. The bug, it fixes, makes the compiled code produce an incorrect result for an arithmetic operation. And you can use it to create a type mismatch and then exploit it like a classic typer bug. So the cheat compiler bugs are so powerful, and they have been so thoroughly studied, as Amy and Samuel's presentation should have convinced you, that it literally takes minutes or a few hours in a really bad.
So he just made mention of Amy and Samuel's presentation, so I'll just shout out the fact that we'll actually be covering that talk. I think we're planning to do it next week, same time as these streams.
That case to repurpose your existing exploit for a new bug. That's exactly what we did. So with the renderer quickly out of the way, we moved on to the Sandbox escape. Unfortunately, we couldn't find any.
And again, apologies for pausing, and apparently OBS doesn't like unmuting me anymore all of a sudden. What I had said during that was he just mentioned Amy and Samuel's talk. We'll be covering that next week at what time was this? At 6 p.m. Eastern, I think. Basically same time as these streams. We'll be doing it again next week, doing that'll be one of the talks we're covering.
Days that affected Chrome OS and were easy enough to exploit, so we had to look for our own vulnerability. Our choice of the area to focus on was inspired by an in the wild bug we investigated just a few weeks before. And that area is the layer that translates IPC types in Chrome into native C++ types. This is done automatically most of the time, but in some corner cases, the developer has to implement the serialization and deserialization manually. So Our experience performing variant analysis on an in the wild issue almost always leads to the discovery of at least one related issue or a variant. This is not the case for any other type of external or internal bug report. Almost like people selling capabilities don't like bug collisions and choose to look for bugs in more obscure areas. So on this slide, you can see the definition of a Chrome IPC data type called data element, written in Mojo IDL. Data element is essentially a union type, but it was defined as a regular structure emulating a union with a few shared fields. On the right, you can see it redefined properly after the fix. The problem here is that several data element subtypes need to track the length of the element, but one of the subtypes, namely kbytes, already stores the length internally, and the deserialization code doesn't check that the two values match. This is the deserialization function. Out points to an object of the native C++ data element type. Out buff is a nested vector that's initialized with the data we control, and out length is initialized with an independent value, essentially, which we also control. Of course, the code that deals with serialized data elements, with deserialized data elements, fully trusts the length field. We unfortunately can't sit on 0 days at Project Zero, so we had to report the issue to Chrome before continuing. But the bug seems pretty powerful, and it's a classic primitive. We have a buffer in which we control the fake length, the actual length, and the contents. Unlike the original in the wild issue, though, a privileged process will never write anything to the buffer. The only thing it can do is to send the contents of the data element to a remote server as a body of an HTTP request. Luckily for us, our colleague Stefan has discovered a technique for exploiting info leaks in privileged processes. Actually presented it at this stage in the last OffensiveCon. It turns out that in Chrome, you can talk to an IPC interface as long as you know it's a 128-bit secret port name. Well, to be honest, you can no longer do that. Stefan has finally killed the technique in Chrome 99, so in a few weeks it will become useless. The vulnerable code though handles HTTP requests, so we must be in the network process. This event has some advantages because if our sloppy exploit crashes the process, it will get restarted automatically without notifying the user. But there are not too many privileged interfaces in that process, and most of them are created early in the process startup. So we couldn't groom the heap well enough to just steal the interface name of our choice with a single info leak. The best strategy we came up with was to spray the heap with the target port name by repeatedly calling a method on the target interface. And we can do that directly, obviously, but we can ask the browser process, or we usually can find a method that will trigger some method in the network process through the browser process. And from another thread, at the same time, would trigger the bug, basically collect everything that looked like it could be port name and check if it's the port we need. The process would take some time, and it was also dependent on the internet bandwidth because we actually had to send the leaked data over the network. Yeah, and Justin could just close the tab before it finished. Also, heap spraying a lot of stuff from multiple processes, multiple threads is CPU intensive. So if we didn't succeed quickly enough, the fans on the target device would start spinning 100%, which was slightly suspicious for
can't get much more of a literal definition of noise than that. So, yeah.
A little noisy. Interesting, like, consideration, like, not something I need to think about really in anything I've done is fan noise.
Yeah, definitely like an indicator though. Like if you're not doing anything intensive and you notice the fans ramping up, yeah, could be suspicious.
Yeah, or, I mean, it's Chrome. It can spin up anytime it wants. I
That
guess
might be true too.
that is more on the RAM side, I guess, but whatever. Kind of jumping back a little bit, I do think this, I guess they called it Project J. I'm not sure if that's actually what, like, Google calls it, but I did find that to be an interesting, I guess, project or game inside the company to have, trying to hack your coworkers when they're leaving the team. Well, trying to compromise and get their password when they're leaving the team. Seems
It
like
is
it would
pretty
be,
funny.
yeah, like, I mean, some places I've worked had sort of similar things, like just the idea of messing with somebody, like if they leave their laptop open, of course, and like that is just like a common, or as like a common practice within the company to like lock your computer, not like dropping a Chrome exploit. Like the level of this is kind of insane, honestly.
It's a little more intense, yeah.
Yeah.
I do kind of wonder what the rules of engagement are a little bit. Like I have to imagine there are some lines you can't really cross with popping your coworkers with ODays, but yeah, it's funny because I don't remember really hearing about like anything about this, and I know a few people who work at Google, but yeah.
Yeah, I mean, it might also be the type of thing that doesn't necessarily come up too much.
Yeah. That's what I was
Yeah, I mean,
thinking.
it's on like a completely different level, because I've heard of things within like security teams to do that sort of little, the little jokes with if they leave their computer open, like very minor things, and this is just kind of insane, but also kind of cool.
And obviously good for Google because it can uncover new techniques and new vulnerabilities that they can patch. So
Oh yeah, I
yeah,
mean,
there's obviously a production element to it too.
it's a good practice, and just like as the individual is participating, you're aware of the security, and you're always kind of needing to think about it, or thinking about at least a little bit more, being more aware. It is gamifying that security awareness aspect. But all right, let's restart the talk.
Our target. We didn't have enough time to find a better bug, so we just came up with a workaround. Decided to hide the process after we successfully exploit the initial issue, the V8 bug, then wait and continue at a later pace, hopefully without triggering too much attention. Yeah, by default, the renderer is terminated shortly after the page is closed. We can avoid that thanks to shared workers. The shared worker interface represents a specific kind of worker that can be accessed from multiple windows at the same time. And as you can see from its module interface, the shared worker and the process it lives in will be terminated after the last connection to it goes away. From a compromised renderer, if we have an arbitrary read-write, we can just essentially connect the worker to itself, creating infinite loop and preventing the process from being terminated until the whole browser is restarted. The trick worked pretty well. The laptop would no longer turn into a jet plane. We just needed to find an IPC interface to attack. This is a network service, the main module interface of the network process, used solely by the browser process, and it has one curious method that allows you to set up the full path to external GSS API library that gets loaded when Chrome receives a 4.1 response from a web server. That's right, the method just loads an SO of your choice. Very convenient. All that's left is to drop a file on the target's disk. Yeah, there's a lot of different ways you could use to drop a file. You could abuse HTTP cache, force a download, but there's an even better way, because the IPC interface that acts as the backend for the HTML file system API has the method getPlatformPath that just returns you the full path to your web file system file. It's obviously not exposed to JavaScript, but nothing prevents a compromised renderer from calling it. So we put all the parts together, popped calc, and we'll learn the hard way that Chrome OS isn't Linux, because in Chrome OS, the user data folder, which is the only folder we could drop files in, was in non-executable mode. We were really running out of time at that point, because the new Chrome version came out with both of our bugs fixed. Justin essentially just needed to reboot his laptop. Since our goal was just to steal the password, we will settle on using another privileged method in the same network service interface to temporarily redirect all traffic to our proxy server and make the browser trust our certificates. Then we backdoored the login page by requesting it from the exploit, responding from our proxy, adding a couple of very aggressive HTTP cache headers and a bit of our own JavaScript. This is the final exploit flow. We have successfully stolen the password twice, actually, because Justin couldn't properly clear the cache for some reason the first time. The exploit has, well, a nice property. It's data only. Both of its versions didn't have to run any shellcode, didn't have to call any native functions, all thanks to Mojo.js. And Mojo.js is a feature of Chrome that exposes part of IPC to JavaScript. It's used by internal Chrome pages, but in a compromised renderer, it can be enabled by just overriding a flag. So why are we talking? The browser people in the audience might ask, why are we telling them about a technique that has been public since 2019? So because we want to show how fun exploitation is once you can do it from JavaScript. But this is an ideal case. We just got lucky with our Sandbox escape. That is, the interface the bug was in, and all the interfaces we used for exploitation were supported by Mojo.js. And in 2022, it's not the case for most of bugs and privileged processes reported to Chrome. Mark will talk about why it's not always the case and what to do about it.
Okay. Yes, it works. Good. Yeah, I hope everybody had a coffee during the break, because it's going to get much heavier from here on. And I don't have enough time to really do a full intro to Mojo. I did try to make those slides, but it was just too much. So the rest of this talk is basically we're going to follow a little journey into Mojo and JavaScript and how the two mix together. And it's kind of following a process that I went through after we finished analyzing the second Sandbox escape that Sergey mentioned before from in the wild stuff, where I said, oh, I don't understand Chrome Android Sandbox exploitation anymore. I need to go write an exploit for this bug just to, like, get that familiarity back. And then I got talked into, oh, well, you should write the exploit in JavaScript, and oh, actually, you should make the whole thing data only, and it just snowballed from there. So yeah, quickly take a look at some Mojo IDL. So this is basically how your Chrome developer describes the interface that their service exposes. We've got a super simple example at the top. It's a small interface. It has one function. It takes a string argument. It returns an array of integers, right? in practice, the Mojo IDL lets you specify like arrays of maps of integers or arrays of maps of interfaces or all sorts of crazy things. But we're not going to go into that really today. The bottom two examples are a little more interesting. So those would be interfaces which, where they actually return a handle to another service. And there's an important difference between the two, which is the top one, it returns a remote, and a remote is like a service binding which has its own message pipe. And an associated remote, that is like a handle to a service where you're actually sharing a message pipe between the parent interface and the child interface. And we'll see some examples of that in a little bit. But first, I've got a kind of, the writing's kind of small. Anyway, 10-mile view of the Mojo implementation in Chrome. So starting at the top, we have this client language layer. And actually, you can implement Mojo code in JavaScript, in C++, in Java, and in theory, whatever other language you would implement this top section in. And actually, the top layer in this orange section is automatically generated from that IDL code we looked at a minute ago. Underneath that, we have a C API layer called the Mojo System API, and that's where one of those exploits we saw was actually hooking into to manually do their Mojo exploit. And underneath that, we have a load of C++ code which actually implements all of this, and the platform-dependent stuff to actually send these messages between processes, which is obviously different on each platform.
So that is one thing with these IPC mechanisms, especially in things like Chrome, is there are so many layers of abstraction that are going on here that it's really difficult to keep track of everything. And that's kind of what he was saying, I guess, when he first got up on the stage for doing the second part of this talk, is like it's difficult to even keep track of in the slides in like a time without going like over time. Like it's just, yeah. So it'll be interesting to follow.
Browsers have a ton of complexity to them. It's a hard area to kind of get into and get up to speed in, because there is just a ton of side knowledge, like even compared to like kernel exploitation. Like at least with the kernel, the problems are kind of well understood already, like they've been around for a while, whereas in the browser, like things are moving, I think, a lot quicker. And so that's just a lot more added complexity.
Yeah, I've said it before and I'll say it again. I don't think there is a harder exploit target than browsers. I don't think there's anything more difficult, at least right now.
Yeah, and at least when we're talking about the modern hardened browsers, I'm sure somebody's written some terrible browser that isn't that bad to exploit, but I mean, Chrome's really the big one, I think.
Yeah, talking more about like cutting edge browser research there.
Yeah, actually, you've done a bit with like WebKit, so I assume the WebKit being used with like the PlayStation stuff. Does that still apply over to like Safari WebKit and like iOS? Obviously, you have the platform differences, but like at the WebKit layer.
So there is some stuff that ports over, like a lot of the underlying objects for JavaScript objects, like let's say, JS ints and things like that, are fairly portable across different browsers. What they're talking about here, though, is less at like the JS engine level and more at the IPC level, which is like at the renderer. That is quite different, I think. That's getting into like Mojo as a system, I think is pretty unique as far as like browsers and IPC goes.
Yeah,
So,
I got that. I was more just drawing the connection at the web, like just
yeah, at the
when we were
engine
talking.
level.
Yeah, because we were talking a bit more generally just about the browser exploitation. I was just curious on how much transfer there was there. Not so much trying to tie it into this talk specifically.
Yeah, at the engine level, there is quite a bit of similarity because like Chrome originally forked from WebKit. Now that was a long time ago. Chrome uses Blink, which has changed quite a bit, but the underlying like fundamental concepts are for the most part the same. But yeah, when you get into like the renderer level and stuff, that's when it starts to really deviate, I think.
Yeah, makes sense.
So, Sergey said a minute ago, like, yeah, this Mojo.js thing, it was talked about in 2019. I think I was maybe the first person publicly to talk about doing this. I don't know if anyone was doing it before, hands up. Yeah, so you have a renderer bug, there's a flag you can flip, you can reload the frame, you get these JavaScript bindings, you can talk Mojo. It's really sweet. Your exploits can be data only, right? So what does this JavaScript look like? This is just a small snippet of code to interact with the blob registry. Anyone here who has written a Mojo exploit probably used something like this, because it's super convenient for heap manipulation in the browser process. But yeah, the top 3 lines, we're creating basically a handle to a blob registry. We're binding that to a message pipe, and then we're sending that message pipe to the browser process and asking the browser process to actually connect that to the blob registry. The middle bit, this is just setting up arguments, whatever, some data, right? And then we have effectively a second IPC call at the bottom where we're actually sending a request to this blob registry handle we created a minute ago. So far, so good. And for the 2019 exploit and for the one that Sergey just discussed, like this is enough. We can do everything we need. But he also said, yeah, there are some reasons why you can't use this. And shortly after that blog post, we saw like a lot of reuse of this technique in exploit competitions, in VRP reports, and it's kind of dropped off. Like a lot of the bug reports now, and as you saw all the in the wild stuff, there's either renderer patches or there's like loading an ELF file or whatever, right? And there's a reason for that, and it's kind of illustrated here. So on the left, we have like 6 interfaces. These are possibly not all, but nearly all of the ways that the renderer requests a service binding from the browser process. And the bottom 2, which are colored in orange, they're actually exposed to Mojo.js. And the top 4, they're all channeled through this one big message pipe, this associated message pipe. And this isn't exposed to Mojo.js. There's a reason for that, which is that at this top level in the implementation we saw before, like the orange layer, you can't really share a single message pipe between multiple languages, because how would you know which of those languages was supposed to be reading the next message you got on that message pipe, right? It's just the way it's architected, it's not something that conceptually really works. In addition, it's actually not something that Chrome needs for what they use Mojo.js for, so there's really no reason that they would go and support it. So we need to find a way around this first, because the bug I was looking to exploit is in a frame-associated interface, which is up there in that top blue section. So we can't share a message pipe between JavaScript and C++, but we can man in the middle a message pipe between JavaScript and C++ and just proxy all of those messages through JavaScript. And you think like this is a lot of messages. This is like all of your frame manipulation, all of your DOM, like everything goes through this message pipe, but actually it works pretty fine. It's even better if you do it in a cross-process iframe and not the top-level window, because then you don't have any UI problems at all. So at this point, you say, okay, we're done. We have Mojo.js support for all of the interfaces. We can go and write our exploit. But one of the things that I've been talking to Chrome about, one of the things that came out of that 2019 work was people saying, okay, we should just get rid of Mojo.js. Like, we should just not have this in any of these renderers that don't need it. And I said, well, it's not like, I mean, you could do that, but it won't prevent people from doing this. And I said, like, you can just re-implement Mojo in JavaScript. Like, it's not such a big problem. And then we wondered, like, can you? Like, can you do that? Like, we know JavaScript engines are super powerful, right? We know you have so much control, but can you really just re-implement Mojo in JavaScript fully data only and just, not need Mojo.js at all? I didn't start with that, right? Like, I'm not going to do some huge engineering project, just straight jump in. So I said, okay, like, what's the simplest way that I could go about doing this? So quickly, we'll just talk back about renderer exploitation. So I think everybody who's written like a browser exploit or like a renderer exploit will be like, yeah, these are pretty reasonable primitives to get from a JavaScript engine bug, right? Like, not your first order primitives, but your second order primitives, right? So you've got two type confusion primitives, you've got an arbitrary read and arbitrary write. Now, this V8 heap sandbox thing, right? Maybe this arbitrary read, arbitrary write is going to become hard. Who knows? Certainly the bottom two, we would hope that with maybe in 5 years' time, 10 years' time, we have super robust CFI, we have ACG everywhere, and like these primitives are looking kind of questionable, maybe. I don't know. I would like to see that future, right? Is it going to make a difference for our sandbox escapes? So, yeah. So where do we start? Well, this is where Mojo.js actually sits in this implementation diagram, right? And it's very, very close conceptually to the blue layer underneath. So this is going to be the easiest way to sort of bodge ourselves together a new Mojo.js. And it turns out it's like pretty easy. So using your function call primitive, you can pretty much just write some JavaScript that mimics Mojo.js, and 90% of this whole thing just drops out pretty easily. However, there is another 10%, right? And I guess I need to explain briefly what a trap is. So we've been talking about message pipes and sending messages between processes, but Mojo doesn't just poll message pipes to see when there is a message ready, right? You need something like select or some concept like this, because you have hundreds of message pipes per process. So trap is like the Mojo native equivalent of select. And what a trap is, basically you register a handler, you attach it to a message pipe, and when that pipe becomes readable, that trap will fire and your handler will get called. But the problem for us here is this handler is a function pointer. And you can't really just have a function pointer to a JavaScript function. And I'll admit that I did actually spend like maybe a day trying to think of like how I could arrange things in such a way that I could have a function pointer to a JavaScript function. And then I was like, this is really stupid. I need to move on, and I will just throw some shellcode in here. So this is the first implementation, right? We have a handle to a message pipe. We have a watcher. It's going to watch that handle. We're going to add a trap in, and we'll point that call back to some shellcode. And what will that shellcode do? Well, we want this to be fairly simple, right? So we'll just have a big byte array over in our JavaScript, maybe an old space, something like that. And when that trap fires, the shellcode will just set the signal in this table, and we can pull it from JavaScript, and we can deliver our callbacks. Yeah. So where are we at? So at this point, we're feeling pretty good, because we have a complete polyfill for Mojo.js, and we're like, well, if they remove Mojo.js, who cares? I still have my exploit written in JavaScript. It's not a problem. But it's not really future-proof.
Yeah, so kind of want to comment. I feel like the use of, he mentions the primitives a little bit ago that he's using for this, and the two at the end there, the call and the get shellcode pointer or get pointer shell, whatever it was. they almost feel like cheating for a data-only attack. Now, in fairness, this is in JavaScript, so like it is data-only. JavaScript is just insanely powerful, and so even at data-only, you can still do these things. But like normally, when I'm thinking about the data-only, I don't really think about having that quite that level of primitive. And I think actually he's going to get into the future proofing because those are most likely the primitives that will disappear in the near future, and you will have to work more on just the data side.
Yeah, data only here, you have to keep the context in mind. It is a little bit more like taking advantage of the power of JavaScript a little bit more than I was maybe expecting. But I mean, it's totally fair. Like that's, you kind of have to weaponize the browser against itself in that way when
Yeah,
you're exploiting targets like this.
so the browser literally has this feature to execute code, being just being the JavaScript in general, not even necessarily JIT, but so like it exists there. It's absolutely data only. I was expecting a little bit more focus on the data. I'm not all that disappointed so far or something. Like he's obviously done some really good work here. That's beyond me for any sort of browser stuff. But yeah, I mean, I'm curious to see where it'll go now, but those do feel like the primitives that are most likely to disappear in the near future, so figured I'd call that out.
Proof in terms of mitigations, right? And certainly not CFI compatible. I mean, I guess you.
Yeah, of course, he goes right into it. Those aren't CFI compatible, which is exactly why they're most likely to start disappearing.
All can probably produce those primitives right now, so I guess you don't care that much, but maybe in 10 years. I would like to think that those primitives are going to become more hard. And this idea of having shellcode in there, right, maybe with ACG and JIT-less mode, like this is already kind of... So it's the first thing we want to do. We want to get rid of the shellcode. Yeah, I had to think, this was like my biggest worry in this whole project, right? How am I going to get rid of this shellcode? And I looked at a lot of the web platform, looking for places that Mojo is used and might be useful. And I found message channel. And so message channel is like a normal JavaScript feature. If you're familiar with post message channel is basically a way that some JavaScript code can create a new channel, and it can send part of that over post message so that you have a separate communication channel between two origins or two contexts, maybe a worker and a main page or an iframe. And under the hood, that channel is just a Mojo message pipe. So we replace our trap with a message channel pair. And if you can see, like, it's kind of awkward to point over there, but like this pair of message ports, they're effectively connected through some native code to a pair of message pipes which meet in the middle. And obviously, if this message port is going to work, it needs to get notifications when those message pipes are readable, right? And that's exactly what they have, right? So for each of these message pipes, there is a trap which is waiting on that handle. So can we just move that handle to point to our other message pipe and get notifications when that message pipe is ready for reading? Yeah, we can. I mean, modulo some gymnastics, but yes, we can, and it works. One of the problems here is that this message port interface, right? It doesn't send raw Mojo messages, right? Like we can't just send whatever we want over that. It has some structure it expects. So we have to actually make sure that when our top message pipe, the one that we're actually interested in kind of polling, becomes ready for reading, well, this other message pipe has to have a message that's ready to be read, otherwise everything's going to get really confused. So yeah, we have to do a bit of gymnastics, but it's not actually as hard as it looked. So at this point, I'm like, okay, this is going to work. I think this is probably when I submitted the CFP. And I'm like, this is going to be, and then fast forward, you know, whatever. It's getting close to the conference. It's not actually finished. Because it turns out, actually, re-implementing message pipe is not as easy as you might think. There's a lot of code there. And if we go back to our little system diagram, it's actually kind of difficult to interact with the Mojo implementation at any layer other than the very bottom layer from like JavaScript in this data-only way. And the reason for that is just that almost all of these layers, they're kind of a pass-through. Like they just call directly into the layer below. So if you're accessing this in parallel, like obviously the JavaScript thread doesn't normally send Mojo messages like directly. So the IO thread is constantly interacting with Mojo channels. We need some actual concurrency primitives. And the only place there's any locking or queuing or anything useful like this is right down in the bottom. So we're going to end up writing a lot of C++ in JavaScript. But before we do that, we'll take a look at what things look like at this very bottom layer. So this is basically, if we look at that JavaScript we wrote earlier, this is the first message which actually gets sent over the pipe between the two processes. I'm not going to go into it in detail, but the top green section is a load of different headers. The big red section is the metadata associated with the message pipe that's actually being sent. And all of the orange is actually generated from the IDL code. So that's not something that we have to build ourselves in this case. And again, we go back to like fast forwarding. I'm not going to show you all of this JavaScript code. I will hopefully release it at some point when I've removed all the to-dos. I'm not quite there yet. But this is std unordered map find in JavaScript and compatible.
This is just absolutely insane. Re-implementing C++ things in JavaScript like this. I mean, it's par for the course for P0, I guess, but you don't really see this kind of insane technique being applied in other places that much.
Oh, not yet. I mean,
Yeah,
he is
maybe that's
moving
the way
this.
it'll go.
Yeah, I mean, I was just saying, like, oh, he's using a little bit more than I expected in terms of the JavaScript engine, and then where does he go from there into not doing that? And this is what's involved with that.
Yeah.
And compatible with libc++. And in order to get this message pipe stuff working, right, we're going to re-implement like half of base and half of libc++ just so that we can interact with the data structures safely or correctly. So the process I took when I was doing this, I would say, was basically like, I'm going to go rewrite a load of C++ code in JavaScript and test it. And then as soon as I reach a point where I find something really hard or awkward, I'll just put a function call, because I have this call primitive, right? And I put it to do, and I'm like, later I'll come back to that. And at this point, we have like 3 to-dos left, and they're all kind of hard. So the rest of this talk is going to be like, how do we solve each of these awkward problems in this data-only environment where we don't want to actually need to break CFI? And the first one, which I guess some of you might have guessed already, is locking, right? We need to interact concurrently with these C++ data structures from JavaScript. And the first time I did this, I just like iterated through the lists, and the exploit worked like most of the time. It's like nobody modifies it at the same time, we're all good. That's not really ideal. So yeah, we want to take locks, we want to drop locks. Taking locks, I mean, it's a spin lock, right? What can go wrong? I know user space spin locks are frowned upon, but for our purposes, this will do fine. So this is how you unlock a lock, right? Yeah, kind of. So in this case, and this is what happens maybe 9 out of 10 times, right? everything is totally fine. I'll add, you can actually do some extra tricks. So if you modify the internals of the mutex, you can make it so that other threads will spin on it for a bit first, and some things like this that you can get it kind of like, your exploit will only stall maybe. This happens. So this is the other case. This is the bad case. JavaScript is holding a lock. C++ code comes to take that lock. The C++ code is like, okay, I better wait. The JavaScript code is like, oh, I'm going to unlock that. And the IO thread is gone, right? Like the IO thread is just going to sleep until the browser process kills us because we're not talking to it anymore. And I went through a sort of denial phase here where I was like, somewhere in the Blink code, I will find a function which will acquire a lock and then call into JavaScript. And then when the JavaScript returns, it will release the lock. Surely somebody has written this in Blink. There is so much code. And after a day of grepping through, I was like, again, you're being dumb. Like, there is just no reason that, like, it would just be so broken that it's, like, impossible that this would exist. So I found this instead, which is not that. This is part of the Web Codex API. And all there is to really say about this is we have this small object. This small object contains a mutex. When we call this function, that mutex is acquired and then immediately released. And this object is actually referenced from the video frame object, which is actually directly exposed to JavaScript. So this is one of the bindings objects. And this object has a pointer to that frame handle object. So by calling this timestamp function, we can get a pointer followed to lock a mutex and then unlock the mutex. So this gives us a primitive basically to lock and unlock immediately a mutex. And that's enough to actually fix our problem. So we're sitting here, the IO thread is stalled. When we unlock the mutex, we can actually see somebody else is waiting for us to release that mutex. And we need to now add another thread, the left gap kind of foreshadowing that. So we add in a worker. And what that worker will do is forcibly unlock the lock, so just set it to unlocked, and then start spinning using that primitive to lock and unlock this mutex. And while it's going, we're just going to race it in the main thread, and we're going to try and flip the bit which says somebody else is waiting on this mutex. And yeah, in this case, we lost again, but eventually the main thread will flip this while the worker thread is holding the mutex. And then when the mutex is unlocked, the IO thread wakes back up and we can continue. Yeah, pretty cool. So, second place. So we've got locking, we've implemented all of this stuff, but at some point we have to actually send these messages. And on Linux, there's actually two ways they're sent. One is shared memory, that's easy, but that doesn't work for all messages. So we actually need a pipe write. And writing to a pipe is a syscall. If we look at the actual channel code, there is a fallback path that will get triggered basically if the pipe is full. So you could say, well, like, okay, let's just send lots of messages, the pipe will be full, and then we can quickly, but like, that's going to cause loads of allocations. We're trying to write an exploit, right? We don't want to like DOS the browser process just to send a single message. Like, that's not going to happen. So we need to find a way, basically, to mimic the bold function call at the bottom here, wait for write on IO thread, no lock. And that, initially, I just used the function call here. But if we look at what that function does, is it's just going to post a task onto the IO thread. Now, post task itself is not tremendously complicated. Again, there is some locking, there's some sort of lockless magic and things, but eventually you're just shoving something into a queue. I would note that this is probably the most sketchy part in terms of future mitigations, because we do have to fake a C++ object that contains like a function pointer, right, effectively. So maybe you could imagine some current mitigations that might try to do something to stop this from being easily forgeable. I don't think that any current implementations would make this actually very hard, but if you do, feel free to talk to me about that later. So all we have to do actually is create this fake task and add it to this queue. I did spend 2 days debugging why the exploit didn't work after I did this. Even though these tasks were getting run, the exploit didn't work. The exploit didn't work because the tasks were getting run really late. Tasks were getting run really late because the IO thread wasn't doing anything. So there is a load-bearing cookie set in my framework that just causes the IO thread to do some work so that it picks up these tasks and sends the messages. And that's all you need to do, just to force this message queue to exit so that it actually picks up this task. So we can send messages. And we're left with really one problem left. And this is kind of a tricky one because, again, maybe if you've been thinking, well, maybe that's a bit much to expect to follow. And anyway, we have these traps that we discussed, right? And if we receive a message in JavaScript and it needs to be dispatched to the C++ code, we might have to fire one of these traps. But we already know these traps contain arbitrary function pointers. So like this is the code where it would happen, right? So if we'd received a message on a message pipe and we actually need to dispatch that message, and it turns out that that's the next message that message pipe is waiting for, so that message pipe goes from non-readable to readable, then that port status has changed. We need to actually fire that trap, which means we have to call this function pointer. So there are basically 3 cases here. So the first one, we have our exploit code in JavaScript. It's sending some message through this proxy. It's going to another process. If we get a message back, it's going to the JavaScript, so we don't care what the C++ code thinks. It's not a problem. We have our exploit code in JavaScript. It's sending a message to the local C++ code. This is a problem, but we don't care because you're not trying to exploit the local renderer, right? So why would you send this message? Unfortunately, this case we actually do care about. So this is when we're proxying a message from the browser process to the local C++ code, and that would make a message pipe readable. And then we need to actually dispatch this trap. We need to call this function. One way around this would be to literally re-implement the entire renderer in JavaScript inside the renderer so that you could just dispatch this to your JavaScript implementation of all of these interfaces. I would not recommend trying to do that, but again, if you do it, I would love to see the code. What I actually did was complain to my teammates about how this was impossible. And as often happens when you say something like that, Jan Horn was like, it's really easy. What are you complaining about? You just need to add more indirection. So indeed, double down, add another renderer. Suddenly, all of these messages that were process local and problematic, now they're not process local, right? Every message we want to deliver locally, we just bounce through another renderer. The problem is solved, and the C++ code just handles it for us. Yeah, and at that point, the end. We have a full, effectively mitigation-safe Mojo.js future-proof implementation of Mojo from JavaScript, and you can go on and write. I mean, I never actually got around to writing the exploit because it took me so long to write the framework that I was like, oh, it's OffensiveCon already.
He mentions that it took him so long to do it, but most of the time when he's been giving any time frames for it, it's like, oh, I, debugged this for a day or after spending a day debugging or whatever. So he made it sound like this wasn't actually very long, and I was going to comment on that at the end, but sounds like he spent more time on it than it might have sounded like, which I would have expected.
Already. So I guess I'll probably go and do that at some point, but yeah. I do intend to release the code, at least the simple polyfill should be releasable fairly soon, but I'm not making any promises. I would also like to write some blog posts about details, but again, there is so much stuff to do, so. But yeah, any questions?
So some very cool tricks there. It was pretty difficult to follow without having any background really in like the areas he was talking about. I got the general like the gist of it and the ideas and whatnot, but yeah, some of the implementation details he was going over there, I kind of just glanced over, to be honest.
Yeah, I mean, didn't really have a ton to say during this one because it is kind of outside of, well, my own experience and just like there's
That's
a
not
lot
most
to
people's
it.
experience, to be fair.
Yeah, I mean, it was interesting. I got the gist of it, but like there was nothing I could really comment on besides, you know, how interesting or cool some of these things that he was actually approaching were.
Yeah, and just a talk that emphasizes what Xenosign said in chat, which is browsers in general never seem to get any less mind melting, insane stuff, but insanely inspiring. Yeah, I mean, when you see like such complex exploit frameworks and stuff being employed here, it's hard not to think like, wow, what I'm working on seems very mundane by comparison. So kind of gives you, I guess, inspiration to go back, and your problems that seemed significant before you watch the talk don't seem significant anymore. But yeah, I mean, it'd it'd be interesting to see if some blog posts come out from this. I could totally see them. Like, Hero's been kind of a machine this year with putting out these really in-depth posts on like the technical details. So yeah, the talk didn't end up covering what I was suspecting it might. Um, those who watch the podcast might remember. I think it was last month, maybe. I don't remember the exact time frame, but they talked about an iOS chain they had, which was like a data-only sandbox escape with uh, Objective C. So I didn't know if they were going to go in that direction, but no, they didn't. This was all focused on Google stuff. It wasn't talking about iOS, but kind of somewhat similar concepts being applied there. Obviously not the same, but there were some similarities that I could draw. But yeah, I won't go too much into that here. Partially because I don't remember everything from that Objective C sandbox escape, but yeah, I mean, lots of cool techniques being used here. Will be interesting to see how long this technique survives. He was kind of saying there that this was like a future-proof technique that's kind of evades all the mitigations that are in place at the moment. So yeah, I mean, could see this being reused in other exploit chains, kind of like what he was saying earlier with a previous technique that he had that got reused.
Well, I'm not sure
But
if he's released too much of this yet. I did just try and Google to see if there has been more of a release of what he did here, but I couldn't find anything. That said, I was also trying to pay attention to the talk, so perhaps I just overlooked it or missed it so far. I mean, the idea, like, it does seem like it's quite a bit of effort if somebody does have to go and re-implement a lot of especially on the JS side for, re-implementing all of those things. I do want to see it, like, his re-implementation of, the C++ library would be interesting to see in JavaScript, although that code didn't look pleasing to read. I mean, not that he wrote bad code, but the fact that that's JavaScript code for these things is, yeah, I mean, I wouldn't want to need to debug that code. I'll put it that way.
you know what would be a really cool project? Something that could automatically take C++ code and like transcode it into like JavaScript. That would be insane. I don't know
Doesn't
how many technical hurdles you would get into trying to do that, but that could be a talk in its own right.
I feel like there is something that does that kind of. Like not perfectly, but that does take an approach at that. Because I feel like I remember coming across some project doing that well before WebASM existed. Like before that, I remember seeing a sort of project that was doing that. I don't remember. Obviously, that was quite a while back, but I think something it might be out there. That said, that's probably like C++ has changed quite a bit even since 2011. And I feel like that might have even been either early 2010s or late 2000s, probably early 2010s. So like C++ has also changed quite a bit since then.
Yeah, and one of the areas that is taking advantage of cutting edge things from C++ would be browsers. So yeah, it would probably, I don't know. It'd be interesting to see how easily this could be automated. But yeah, I mean that sounds like a massive undertaking. So we'll have to see if anyone goes into that. But yeah, this talk was. When was this talk published exactly? I went to go get the link, but like you, I was kind of paying attention to the talk and didn't want to get too distracted where it was so technical.
I can pull it up here.
Um,
It's like it was April 21st.
yeah, April 21st. So yeah, it hasn't been too long. It's only been like about a month. So hopefully that code will go public. But like you said in the talk, it sounds like it's not a guaranteed thing. But yeah, there's a lot of cool code in there that you could explore. I feel like you would really have to dig into it and like play around with it in a debugger and whatnot to really understand, to like fully appreciate what's been done here. Just getting like a surface level talk of it, or even maybe a blog post, I feel like it'd be really hard to understand everything that's going on unless you played with it yourself. So yeah, the code being released for that would be super useful.
Yeah, jumping off to a slightly different topic. Xenosign asks, I wonder, do people that get into it at this level generally focus on a specific subcomponent, e.g. Chakra, JSC, JavaScript core, or are there common things across browser exploitation that people learn? I think when it comes to dealing with hard targets, there does end up being a focus on like your active exploitation being in a particular area, or a particular component, but that doesn't mean you don't have knowledge of anywhere else. Maybe you've done an exploit in other areas too, especially going from like JavaScript core. I believe that was kind of the meta for exploits some years back. So if you've been around for a while, you might have done that and then moved to other components over time. So you'd have that knowledge there. I've used this term before, but like I'd kind of say the knowledge is probably closer to T-shaped, where it's like you have a wider view and then you have your particular areas that you're focusing on at that moment, and then you're able to maybe draw from past experience. But I mean, people do tend to focus in on particular components when it comes to doing, especially like the manual auditing, um, having those areas that they are actively looking at and focusing on.
Yeah, I mean, you kind of have to specialize when you get into these monolithic targets. You can't really be aware of all the components of the browser, especially with like browser in particular. The development is so fast moving. There's new features and entire new code bases shipping like every major update. So, uh, yeah, keeping up with it is really difficult. Um, but yeah, and then there were some other messages saying the Facebook transcoder stuff. So yeah, I know that like Facebook had it wasn't to JavaScript, but they had like C++ to PHP stuff going on. I never really looked at that too much. I heard about it in passing, but I didn't really look at it. I'm not sure how like compatible that was with like the ABI or what they were doing there. I remember hearing that it was a bit of a hack, but like I said, where I didn't look into it, can't comment too much on that.
Did Facebook's transcoder go C++ to PHP? I almost feel like they'd have gone the other route. I wouldn't be surprised if PHP, if Facebook did that, but I was unaware of this.
Oh, sorry, you're right. I think it was the other direction. I think they went PHP and compiled it to C++ for like performance reasons.
Yeah, because I mean, I
not
know
the other way. Yeah.
because they had PHP, or they started off with PHP, then they did Hack. And I'm not sure if Hack is still kind of where they go. Hack being modified PHP easier to optimize over to C++. Oh no, I'm just looking at this transcoder now, the project.
I forget what it's even called. I used to know, but I just
Literally
haven't
like
looked at it for so long.
or at least what I'm looking at right now is literally like transcoder. I'll drop the link in chat.
Oh, okay.
Which looks like it does. So it looks like it has support for some other languages here too. Translation into C++ though. Or is this Python? The middle one is in Python though, because it's got the int. And this is fairly recent actually, so at least not what I was thinking of, but either way, like the sort of project, like these transpilers, like they do exist, so I won't be surprised to see something out there. That said, generally not like feature complete.
Yeah, and when you're talking about what they were talking about here with like porting over a lot of the C++ standard library, that would be a hurdle. You would need something that's close to or fully like feature complete, I think, or you
Okay,
end up doing a lot of manual work on top of it, probably.
Your own mentions there, I meant more the general approach of using an AI language model, which it looks like this transcoder does. That's actually an interesting approach to doing that translation. The things I remember seeing in years past were not AI based at all. They were actually like matching code and translating it that way.
Yeah, that's what I was thinking of too. And then Jordan also said, well, for browser exploitation, you have to be intimately familiar with all of its IPC magic anyway, so it's not that much of a specialization. Well, it kind of depends, because like what they were talking about here with Chrome, you kind of have the popping the renderer initially, which is like, you're talking about like JavaScript exploitation or exploiting JIT or WebASM or whatever. The next phase of going from like the compromised renderer to like a sandbox escape, that's kind of its own step in the chain, right? So I don't know how much overlap you really have in the industry of people doing both, but I think there is specialization between compromising the renderer, then using the compromised renderer to sandbox escape, and then whatever other step you have after that, like trying to privesc to kernel or whatever. I'm sure there are some people out there who do like full chains like that, but it would be pretty insane. I think for the most part, there's specialization going on in different parts of the chain there.
Yeah, I'm genuinely not sure. Because I could imagine, especially being since it's still all inside Chrome, so I see like a really hard boundary between you have like your Chrome code execution, and then your kernel privesc. Like there's a very clear hard boundary there because the knowledge doesn't transfer. Your Chrome knowledge is not. Having exploit knowledge in general can help and all of that, but like your knowledge of Chrome internals doesn't help with the privesc of attacking like kernel or the underlying platform. So I could imagine I could imagine more people having that shared knowledge, but given the complexity of some exploits, I also wouldn't be surprised, teams are working on these things that, different individuals are working on the different stages of the exploit. I wouldn't be surprised to find that out. I just don't have like the intimate knowledge to actually make that claim.
Well, it's just it just kind of makes sense when you look at like all the effort and work that goes into these exploits and how complex they are. Trying to burden one person with an entire chain of complexity like that is just it's a lot for one person to do.
Yeah, and in
even if
fairness,
you're
like
really intimately familiar with the code base.
for a lot of people, for a lot of these exploits, like it's not a single person; it's a team of people who are working on these things also. So odds are different people have just different skill sets that lean more one way or the other. Or at least it's usually, as far as I'm aware, not just a single individual popping like the full Chrome exploits.
Sometimes it is, but most
It
of the
does
time,
happen, yeah.
Yeah, and as time goes on, you're probably going to see more of a shift towards like more team-oriented stuff because yeah, like Chrome is not getting any easier. As time goes on, it's going to get a lot harder. You're going to have a lot more steps in the chain. So, every year that goes by, it's going to become less and less feasible for like a single person to be able to maintain everything. There's just going to be too many hurdles thrown at you.
Flying Object says, unless it's Ian Beer.
He's the exception to the rule.
Yeah, I mean, I with some of the even just Project Zero guys in general, like I wouldn't be that surprised for them, but they also are able to bounce ideas around and like, obviously very smart people working there. And I mean, even during this talk, he mentioned being stuck during the renderer thing where they basically duplicated the renderer, and like Jan Horn point out like, oh yeah, this is easy enough to do in this method that he wasn't thinking of. There's still that teamwork, even if it's not quite what I was mentioning before.
Yeah. All right, but yeah, that was the 2 talks that we're planning to cover today. We will be back next Friday at the same time. The talks we're planning to cover next week are, Amy and Sam's talk on attacking JavaScript engines in 2022. So that's kind of like an update on how much the landscape has shifted since the FRAC paper that was published. I think it was 2016 or 2015 that the attacking
16
JavaScript
sounds
engine.
right.
Yeah, that the attacking JS engines FRAC paper was published. So yeah, just talking about the modern browser landscape, which will tie back into this a little bit. I mean, it was referenced directly in this talk. And then we also have the Mark Dowd keynote about how do you actually find bugs. We talked about this a little bit on the podcast, but only some points from it. And we hadn't fully watched all of the talk at that point. So yeah, I mean, it'll be interesting to cover in a watch party too, and I think we'll have some thoughts on that. So that'll be next week, Friday. It's 6 p.m. Eastern, 3 p.m. Pacific. But yeah, that's all we have for today. So unless you have any parting thoughts, C, we'll wrap it up.
No, I think that's good, and thank you guys for stopping by over on YouTube instead of our usual Twitch.
Yep. So that's worth noting. Yep. Next one will be on YouTube as well. We'll try to do a little bit better with like the notifications. They were a little bit scattered today, but yeah, just keep a lookout on our Discord and Twitter for that. Because yeah, I mean, you can use like the YouTube bell notifications or whatever, but they're kind of finicky. They don't really work that well. So
Well,
I would
unless you
recommend
go and
following
hit
Twitter.
you can go and hit all notifications when you do that, and then you'll get everything, which I assume will also give the live streams. Who knows with Google and YouTube, but it's the personalized one that's finicky.
Yeah. But nonetheless, yeah, the Twitter and the Discord you can rely on pretty well for the notifications. So yeah. So we'll see you guys next week for the next watch party, and take care.